I talked about Rosh Hashanah last year, about the formation of the first stars and the chemistry that led to the birth of the universe as you know it. And then a number of months later, we had a question and answer session in my apartment with my wife about that. And I want to go from the first stars to the first planet and kind of in the process tell you about some of what I consider the joy of science. Now, the first planet, this is me, and I'm doing this work at Columbia, and we have support from the National Science Foundation and NASA. Really, it's your tax dollars that are funding this work. So I want to make it easy for you this April. Just send me the check. I'll talk to the IRS. Everything will be cool.
And if we don't like this, we can complain to our Congress.
Exactly. So this is a picture of Mercury, by the way. This was taken with a satellite that was sent to Mercury about a decade ago. So some of you may recognize this picture. This is the laboratory where I studied the chemistry that led to the formation of the first star. Hydrogen with an extra electron associates with another hydrogen atom to make molecular hydrogen and detaches the extra electron. Very, very fundamental chemical reaction. So I wanted to continue to study chemistry where you had some element X with an extra electron reacting with the same element, making a molecule X2. So two of those atoms stuck together. It's just continuing to extend the research into more and more complex molecular formation. So we submitted this idea to the NSF chemistry program.
I'm interested.
We submitted it again after. When you submit a grant application, it gets reviewed by a panel of peers, anonymous peers, and they provide feedback. So we incorporated the feedback into the proposal, resubmitted it, and so we revised it, resubmitted it. This time we submitted it to not a chemistry program, but a physics program. And you're detecting a theme, right? And we tried again in 2014 to the U.S.-Israel Binational Science Foundation program. And that also got declined. So at this point, we're basically, okay, we have a $750,000 paperweight in our laboratory. We're not able to get funding to do anything with it. And the typical reviews, just to give you a sense of where we were at, this is clearly a tour de force. The proposal details extraordinary. If I can brag for a moment, the PI is an expert, his team is strong, but the motivation is weak. There's no doubt that this is a challenging problem, but there are many problems in physics that are challenging. There does not seem to be a pre-existing demand from theory for these measurements. So this was just not something. This is not where the field thought the forefront was. I disagreed, but I wasn't making the decisions. So the idea that science is always at the forefront is no. Certain aspects of scientific research are considered sexier than others, and they get funding, whereas this didn't. So they were all declined. It's nice to know you're a great writer, but I'm also a professional loser. So where do you go from here? An inspiration, which is part of the joy of science, comes from unexpected places. So one of my colleagues forwarded an email that he received. My idea is to simulate the effects of cosmic rays and solar energetic particles on the surface of terrestrial bodies within the solar system. The samples would be irradiated with protons by an accelerator to simulate millions of years of exposure. All right, that came from a 15-year-old.
Uh,
I wasn't that smart at 15. So I invited this kid, whose name, by the way, Nikhil, means cosmos in Sanskrit, so it's kind of funny. I invited him to come do a literature study with me for the summer. And at the end of the summer, he does what every high school science student does. He wrote a poster for a science fair. And I wrote a grant application. So he emailed one of my colleagues at Columbia who does high energy particle physics. And I do things involving beams of protons. And my colleague was like, well, this is something that Daniel's more along the lines of what Daniel does.
but how did the kid find you? Even
We're all on the internet. We all have web pages. If you just put in Daniel and astrophysics, you find me.
hey, easy.
I don't think you even need to put in Columbia. I think you can just put Daniel and astrophysics. So I started working with George Harlow at the Museum of Natural History. He's a mineralogist. Have you guys seen how the mineral collection exhibit at the museum? He designed it. Yeah, stunningly beautiful. So we submitted a proposal, and I have a track record of being rejected. So it was rejected. But it's a good idea. Like, I gotta figure out somehow to get funding to do what I think is this really great idea. So I brought in Deborah DeMang. She's a planetary scientist. She studies the surface of airless bodies like Mercury, the moon, and asteroids. So I was able to write a slightly better grant application, but not good enough. So I added Denton Abel, who's at the Museum of Natural History. He's a meteoriticist. He studies meteorites. So you think, okay, these are samples from the surface of these rocky bodies that formed Earth. Why are we interested in this? Because we want to understand planet formation not just in our solar system, but in other stellar systems. If there's going to be life out there, it's probably living on a rocky planet, kind of like Burn. So let's understand how they form. I brought in another expert from Columbia. Again. Eventually, I brought in Rosemary Killen, who studies the atmospheres of other planets. And we finally got selected for funding, but then there was a government shutdown. And so we didn't get the money, didn't actually show up until 2018. So we're already 6 years after the idea has started. I'm not stubborn, but I am persistent. So, but yeah, it's just whether you want to be nice to someone or not. So I had one group member from China work with me for a year on this. I had a group member from Germany, another one from the United States. A couple more colleagues from Columbia joined. O.J. Tucker from Goddard, he studies planetary atmospheres. He joined. Shaisha Bu is actually the person on the project right now. And we are very scientifically fertile during this time. She's had 2 children. And I had another group member from Germany. Now I have a group member from Russia, Canada, the United States, and my long-term collaborator from Belgium, who's actually, he and I are born on the same day of the same year. He's 4 hours older than I am. And we're both left-handed. So I encourage all of you folks to get a friend in Belgium, because when they come to visit, they tend to bring chocolate. So I'm talking about not so much about the science. I'm talking more about the social aspects of science, which is part of, for me, the joy of working with all these fascinating, talented people. So, okay, now let's get to the science. Manishtana hakochav halachet hazeh. So, why is this planet, Mercury, different from all the other planets? Kohav halachet. And these are the rocky planets. They're all rocky. They all have iron cores. Earth has a huge iron core. Venus, 50% the diameter of the planet is made up of iron. Earth is 55%. The moon, it's only a third. Mars is 50%. Mercury is a whopping 83% of the diameter of the planet is iron. So, most of these planets have iron on their surface. Mars is red for a reason. It's rust. So why doesn't Mercury have any iron on its surface? We can look at the spectroscopic reflection from the surface, and that tells us about the elemental abundances. So that's the project. That's what we got funded to do, to try to understand what's going on with Mercury. I didn't put any Hebrew in the grant application. I wasn't certain that they would understand it. So we can understand. So the question is, how did Mercury form? Well, if we know what's on the surface of the planet, we can constrain the formation process. But we don't have any, and we don't have any sample return missions from Mercury. But if we can measure the atmospheric abundances, we can link those to the surface abundances. And the atmosphere's got a lot of things you don't want to breathe: sodium, magnesium, aluminum, calcium, potassium, and iron. No oxygen. So, and there are a number of physical processes that form this atmosphere. And I'm going to focus on ions from the solar wind hitting the surface. That's the project. So life would be easier if we could get a sample back from Mercury. Go there, grab some dirt, come back. We've done it from the moon. We've done it from asteroids. We might do it from Mars. But there haven't been any missions. And part of the problem is, as you move towards Mercury, you're going down the gravitational hill towards the sun. And now you have to come back from Mercury. You have to go up that hill. That takes too much rocket fuel. So Mariner 10, some of you folks might remember, was in the mid-70s. The Messenger mission was about a decade ago. And there's a European-Japanese mission right now called Bepi Colombo. Giuseppe Colombo was the orbital dynamicist who developed the complex trajectories necessary to send a satellite from the United States, so from Earth to Mercury. So they named it after him. Now, clues to the surface composition come from telescope observations. This is the Dunn Solar Telescope in New Mexico. I've never been to this telescope yet, but my colleagues have. And this is a picture of Mercury. The black is the planet, and Mercury in this is going across the surface of the sun. It's a solar transit. And what we have here in colors from green to yellow to orange is the abundance of the sodium. And so what this is telling us is that there's sodium in the atmosphere, which suggests that the surface might be made out of feldspar. Feldspar is a sodium-bearing mineral. Actually, it might even be made out of labradorite, so it's good that we have a Canadian on our team. Is the sodium coming from the rocky powder on the surface of the planet? So, how many people saw the Northern Lights recently? One, two, sort of. Yeah, they kind of look like clouds to me. Yeah, too much light pollution here in New York City. But yesterday I was talking to a bunch of high school students, and one of them came up and showed me on her phone a picture of it afterwards. Okay, so we have the planet Mercury, and it's surrounded by a magnetic field, which is being blown anti-sunward by the solar wind. The solar wind are the protons that form the northern lights. And these electrons sort of hit the planet through these magnetic cusps at the North Pole or the South Pole. And they can also hit the backside. So the locations where the sodium hits the surface of the planet, the poles, matches the enhanced abundance we see at the poles compared to the equator.
Just
Please.
question. I think I completely misunderstood what you just said. Did you just say that the northern lights that we see are coming from Mercury?
No, they're coming from the protons in the solar wind hitting the atmosphere of Earth.
So those Caverlo. I thought you said something about. Okay, so I misunderstood.
No, I misspoke.
Oh.
Yeah. I have put 3 errors into my presentation. Okay. And whoever comes up to me afterwards, it can identify 2 of those 3, I promise to buy a beer.
Was that one of them?
You have to find the other 2, or at least 1 more. So Mercury is covered with a loose powder. And most ion beams in the laboratory travel horizontally. And you can't take a loose powder sample and turn it like this because the powder is going to fall. So you have to hold your sample horizontally, which means you have to come in with your ions from above. So that apparatus that I showed at the beginning of the presentation. So this is a picture of the apparatus that we built. This was in 2019. This is 2020, so you can see that the apparatus I showed at the very beginning that we used for the chemistry of leading to the formation of the first stars, that's this leg of the experiment. Notice it's 2.5 meters above the ground. So out of the ashes of that previous project has arisen the Phoenix project. And this is what the apparatus looks like when it's completed. So this was back in March of 2021. We make our solar wind ions here. We extract them and we deflect them downward onto the target. And we collect the atoms that get sputtered off of the planetary analog surface that we have.
Where is that?
This is located in the basement of the cyclotron building at Columbia's Nevis Laboratories, which is in Ardsley-on-Hudson. So it's about 20 miles north of here. You can get there on public transportation. I actually met my wife because of this research. So I got the lab space out in Ardsley-on-Hudson, and I started taking Metro North to get there, and I kept seeing this beautiful woman standing on the platform, and I'm like, who is she? And how can I start talking to her without her calling the police? So it took me a little while to get confidence, but yeah, so I met my wife online. It was a train line, but it's still online. Yeah, exactly. So we just got our first measurements on a powder, which is what planetary surfaces are like. So we're still analyzing those data. But to answer the question as to where this high school kid ended up, he went to MIT. And after he graduated from MIT, he moved to San Francisco and started in a startup company doing quantum telecommunications, whatever that is.
Yeah.
I think it's really small phones.
Oh.
So really, I'm more interested in just having shared with you the excitement and the joy and the frustration of doing science at this point. So thank you for your attention.
I want to draw one very sort of simple analog, and Stephen will agree with me there's a piece of this that reminds me of the rabbis. Yes? Right? There's a problem. We have a problem. The rabbis look at it, they discuss it, and they don't come to a conclusion, which means that they don't pay for a grant, right? That is really what struck me, and something that Dami was talking about, is the lack of coming to a conclusion quickly or clearly, but also that getting to this more spiritual end of this is we are always searching for answers. We are always searching for answers. And sometimes our questions are appreciated and sometimes not, but we're always searching for answers.